This is the pyroCPU. I'm using a program called Logisim to simulate my designed CPU. My CPU is Turing complete and is capable of theoretically performing any calculation, any operation within a finite memory constraint. I will now begin covering each major component of the pyroCPU. This is the program counter. By default, it outputs the address 0, and output addresses go into the instruction memory ROM. When clocked, the program counter increments by 1, pointing to the next instruction in the instruction memory ROM. Normally, it will keep incrementing to go to the next address in sequential order, but the program counter can also point to specific addresses in the instruction memory ROM if the jump signal is on. For example, if this were 5 and the jump signal was on, it would jump to address 5. This functionality will be displayed in future in this video. The instruction memory, also known as ROM for read-only memory, holds each instruction that the CPU will execute. It takes an 8-bit address to point to the instruction and outputs a 32-bit instruction for the CPU. Right now, all the instructions are 0, but if we were to execute specific instructions, we could input the values that we'd want the CPU to execute. So the instruction memory simply holds all the instructions to be executed. The instruction register takes in a 32-bit instruction and splits it to go to other components of the CPU. It splits it into a 5-bit opcode, a 5-bit for register A, 5 bits for register B, 8 bits for the register destination or an address, and for this CPU there are 9 bits that are ignored for future proofing in case we want to upgrade the CPU in the future. The CPU can only understand instructions 0 and 1, but Logisim allows binary instructions to be represented in hexadecimal format. That's why there are 8 digits here. These are hexadecimal digits. But for the purposes of this video, I will throw in human readable mnemonics so you can helpfully further understand what is going on as I execute each instruction. This is the register file. For our CPU, we only have 32 registers. The register file accepts register A, 5 bits, to select register A to read from. It also accepts 5 bits for register B to read from register B, whichever register we select. We can also write to a register using 5 bits. Writing to a register allows the data to be written into that register to write a value to that register. The register file outputs data for the selected registers for register A and register B. This is the arithmetic logic unit. It can perform 13 operations from addition, subtraction, incrementation, decrementation, and bitwise logic for AND, OR, XOR, NAND, NOT. We can also shift and rotate bits left or right. The arithmetic logic unit accepts 2 inputs from the register file. data A for input A and data B for input B. The arithmetic logic unit outputs a result, and that's how you can see the result for the calculations for the specific operation. The operation is determined by the opcode, the 5-bit opcode that corresponds to each operation in the arithmetic logic unit. This is the data memory for our CPU. The RAM, it stands for random access memory because we can access any memory cell in the RAM unit. The data memory, aka RAM, takes in an 8-bit address from our instruction, and it also takes in data from the register B, the data for register B. That's how I have it set up for my specific CPU. And the data for each memory cell is output. It outputs an 8-bit result. You can store or load values into memory. Storing values will simply store specific values into the memory that you choose for the address, and loading will output the data into the register file. The call stack uses the same RAM component. However, it is used for storing return addresses. For example, when you call an address, it will store the return address for that call. It only has a limited amount of space, so you can only return 255 times for this specific CPU. 256, excuse me. You can push and pop values, and the value stored becomes the address for the program counter once popped from using the return instruction. I will now begin covering each major instruction that the pyroCPU can perform. The load immediate instruction takes in 2 operands for the register and the value to be put into that register. For the purposes of this video demonstration, we'll be loading register 1 with a 9 and loading register 2 with a 10 for nearly all of this video. And now we will see what value is going into the registers. As you can see, the 9 just went into register 1, the value that's being written into. And a 10 has gone into register 2. Those are the values we'll be using for the remainder of this video, unless otherwise specified otherwise. The no operation does nothing. It simply ensures that instructions don't immediately conflict with each other. It allows for padding in between instructions, even aid in timing for instructions. I will now demonstrate arithmetic operations for adding, subtracting, incrementation, and decrementation. The first 2 take in 3 operands, the first 2 as inputs, and the third one for the result that will go back into the register, our selected register. The last 2 only need 2 operands for 1 input, and that result will also go back into the register for the third operand. Okay. Our values have been loaded. Now we'll add. 9 plus 10 is 19. Notice how the flags also change to show the status of the results. 9 minus 10 is -1. Notice the negative flag is on. 9 plus 1 incrementation is 10. And 9 minus 1 is 8 for decrementation. And that's it for arithmetic operations. Now we will perform bitwise operations, which simply compares each digit from input A with input B and performs a logical operation on them. We'll do add, or, XOR, NAND, and NOT operations. Our values have been loaded, and now we'll AND, which becomes an 8, OR becomes 11, XOR becomes 3, NAND becomes -9, and NOT becomes -10. And that's it for our bitwise operations. I will now demonstrate shift and rotate. For the purposes of this demonstration, I will load register 3 with the value of -127. -127 has been loaded, and now we will shift left. As you can see, the digit has shifted left, and the digit to the leftmost has been shifted out. Shifting right, the digit to the left has shifted to the right once, and the digit that was here has shifted out. Rotate left, the digit that was here came wrapped around to this side, and the digit that was here moved up once to the left. Rotate right, the digit that was here has wrapped around and went to the left, and the one that was at the left moved up once. And that's the difference between shift left and right versus rotate left and right. The following instructions use memory. We've already seen load immediate, but we'll be talking about load register, store register, and move register. The difference between load immediate and load register is that load immediate stores a specific value into the register, while load register loads the register with the value from memory. Here we go. Our registers have been loaded with immediate values. A 9 has been loaded into memory location 0, and a 10 in memory location 1. Now we'll be loading these values into our registers. We'll switch load register 1 with a 10 and load register 2 with a 9. Ten has been loaded, and a 9 has been loaded. Now we will move registers, which simply means we'll copy from one register to another. We'll copy register 1 into register 2, so register 2 will have a 10 again. And that's it for our memory operations. Call and return use the call stack. We will be calling address 5 and returning. So we just called address 5, and a 2 is stored because we called address 5 at address 1. And when we return, we want to return to address 2 and not address 1, or else it would be an infinite loop. And notice how it jumped to address 5 when we called address 5. If you didn't see that, it jumped to address 5. And that's return. We're going to return to address 2 in instruction memory. And we return to address 2. Normally you would want a halt before the return, because that can also cause an infinite loop. There are a lot of jump and branch instructions. I will not be going over all of them for reasons that will be clear in the last section of this video. I'll only be going over 3 jump instructions and 2 branch instructions. For jump, we will be going over unconditional jump, jump if greater than, and jump if less than. So first we're going to load our registers as usual. Registers have been loaded, and now we will unconditionally jump to address 9. Notice how it's at address 6 right now. It's about to jump to address 9, like so. And now we'll do jump if greater than, jump if 9 is greater than 10, which is untrue, so it won't jump. Now we're going to do jump if less than, jump if 9 is less than 10, which is true, and it will jump to address 0 because that's what I have it set up as. And that's it for jump. For branch, the difference between jump and branch for my CPU is that branch takes in the offset for the address. For example, if you're at address 3 and you specify address 8, it will jump to address 11. Whereas jump, it jumps to a specific address that you specify. Branch will jump to a relative address that is based on your current address plus the specified offset, which is equivalent to the jump address that you specify. So as usual, we will load our registers. Registers have been loaded. We will be testing branch if greater than and branch if less than. This is branch if greater than. This will test if 9 is greater than 10, which is untrue, so it won't branch. And this is branch if less than. It will test if 9 is less than 10, which is true. So it will branch backwards by 1. You can branch forwards and backwards for my specific CPU. And that is an infinite loop. That's it for branch. Our last instruction is a very simple instruction. It simply stops the CPU. This is the halt instruction. When the CPU encounters the halt instruction, it will stop performing instructions, even if there are instructions after the halt. Once it reaches halt, it will stop the CPU. Let me demonstrate. Now the CPU will no longer work. As you can see, the black highlight has disappeared, and it is no longer performing instructions, even if it is clocked. There are no instructions being performed, not even the no operation. One test to see if the CPU is working properly is to perform the Fibonacci sequence. For my CPU, we'll be displaying the first 12 Fibonacci numbers in memory cell 0 using the codes that will pop up on screen if they haven't already. Alright, we'll begin and watch the numbers in memory cell 0. And that is the Fibonacci sequence for the first 12 digits. Remember, this is being displayed in hexadecimal. So you'll have to convert the hexadecimal numbers to decimals, but I should already do that for you on screen if I haven't already. Documenting and creating the .pyroCPU has been very fun for me. It is time to reflect. What I think I could have done better is that I had duplicate instructions that basically did the same thing. For example, my jump less than and jump negative function are basically duplicates. Same with branch less than and branch negative. And for my Fibonacci sequence, notice I've only displayed numbers in one memory cell. That's because I didn't have an instruction that takes an incremented register variable to display each number in a list of its own. So yeah, this is things to keep in mind for any future CPU design. But other than that, I had great fun, and thank you for watching.